So I've provided two efficient search algorithms for the ERM rule that is specific for specific problems, so not general approach. So each hypothesis class may have different efficient search rule. So you have to design or you have to find such efficient search algorithm for each specific problem. Okay, so theoretical computer scientists, their main research job is really how to find such efficient algorithm and how to show the computational complexity is quite good compared to other algorithms. How to compare the designed algorithm with other existing algorithms. That is the main research topic. One of the main research topic, I think. Okay, so let's consider a very simple scenario because usually this is very difficult topic to explain and to understand. So for this class, I wanna use very simple example. The first one is rectangle hypothesis case. So we can define rectangle hypothesis in d-dimensional real space using this notation. So what does the notation mean? Is this. So when we use A1 to AD and B1 to BD and each AI is smaller than or equal to BI, then the point in between AI and BI for all I will have positive response, otherwise we have 0. So for the binary class, we can draw, for instance, in 2D case, we can draw the 2D axis using A1, B1, and this is first axis. For the second axis, this is A2, B2, oh sorry, so this is B1, this is A1, this is B2, A2, and for this finite interval, we can define this rectangle area, and here we have positive response and all the other point will have 0 response. When the ERM rule in the realizable case, so what is the realizable case means? What does that mean? That is, there exists a hypothesis that has 0 test error. We already know what is realizable case, the definition. And the definition implies there exists perfect hypothesis that make a 0 error. So we can easily make a simple such a rule for the realizable case by finding the smallest AI value. It's the smallest value for the specific axis, and we can set the minimum value to AI for axis I and the maximum value to BI. Then naturally this AI and BI will include every training data point having positive response. So we can easily guarantee this approach can find 0 training error hypothesis. What is ERM rule? ERM rule, just select one hypothesis that has the empirical risk minimizer. Then the total learning time is d times n. So here d is the dimension of input space, input domain, and n is the number of training data point. Then we have 0 training error. Okay. Right. So although there are infinitely many different hypotheses, because we can define many different rectangles using different AI and BI values, but the training complexity for the simple learning rule using min and max operation, that just require the d times n number of computation. Okay. But unfortunately, when we do not have the perfect hypothesis, so we don't have the realizable assumption, the realizable case, then solving the ERM problem in the agnostic setting is NP-hard. It's known to be NP-hard. So what is NP-hard? From wiki definition, in computational complexity theory, NP-hardness, non-deterministic polynomial time hardness, is the defining property of a class of problems that are informally at least as hard as the hardest problem in NP. Okay, at least as hard as the hardest problem NP. And then the question is, what is P and NP? So P versus NP problem is a long-standing key question in theoretical computer science. The P problem is there exists some algorithm that can solve the task in polynomial time. So P task, the complexity P task, means there are some algorithm can solve the task in polynomial time. So here the keyword is solve in polynomial time. Whereas NP, we can verify the answer in polynomial time. So the keyword is verified in polynomial time answers. What is the meaning is we can make algorithm f such that fx always make our desired of y, and we can find such a function f in polynomial time. Then the task is p task. The complexity is p. Okay, but we don't know how to find such f, but we can easily verify this mapping is true or not. Then we say this is NP. Okay, we can verify the answer is true or not in polynomial time. Then this is NP. So the question is P equal to NP or P is not equal to NP is a very long-standing question. And if you can make a solution, if you can make answer for this question, then you can be famous and you can be rich. Right. Anyway, so NP-hard is the among NP category task, we say include every difficult task in the NP. So we say when we can solve a task, when we can solve this task, then from this task we can easily solve NP task. Okay? NP hard means when we can solve NP hard task, which directly implies we can solve any task in NP in polynomial time. So NP hard, from this we can say the complexity of NP hard is at least as hard as the hardest problem is in NP, because when we can solve one of NP hard problem, that directly implies we can solve any NP problem. Okay, so in general, when we say about the computational complexity or complexity theory, especially with term of P and NP, how can we say, okay, this problem is NP hard, okay, this is P problem, okay, this is NP problem? How can we say? So there are some famous category of NP problem, and usually we can we make some mapping between the well-known NP problem and our desired task. If there is some mapping, one-to-one direct mapping between NP and our desired problem, then we can say some equivalence. Like when we can solve this problem, then using this property we can solve this. When we can solve this problem, using this property we can solve this. We can make such a relationship between tasks, and from that we can say, okay, when this is NP, this is also NP. When this is NP, this is NP hard. Usually the computational complexity theory use that kind of proof technique, but that is out of scope of this class, so I don't want to go deep for that series, and I want to stop here. Just I want to just explain what is the definition of P, what is the definition of NP, what is the definition of NP hard. Okay. Anyway, NP hard is not good news, and when we do not have the perfect hypothesis having zero error, solving the ERM problem is known as extremely difficult, and the computational complexity will grow very quickly, exponentially, as the dimension degrows. One another example is Boolean conjunction. Boolean conjunction is a mapping from d-dimensional Boolean space to one single Boolean output, which can be expressed as follows: xi1 or xi2 or xik, or not xj1 or not xj2 or not xjr. For some in this I1 to ik, j1 to and jr, so I1 to ik to define I here, so the true statement of x some index, and j indices to define the not xj1, not xj2, and so on. And this condition, what is the meaning of this statement is, so basically the input space is a d-dimensional Boolean domain. So each x1 to xd has value or 0 or 1, false or true. So x1 itself will have value 0 or 1. For instance, if x1 is equal to 1, then not x1 is equal to 0. And or means, so this is not or, and, okay, sorry. So when we have this and sign, basically all the statement having true statement, having value 1, then the output is equal to 1. Whenever just one single element or one or two element having 0 value, false value, then the output is false. Even with one single false statement, we have false. Okay, so hx is equal to 1 if all the x statement is equal to 1 and not x statement is equal to 0. And xx is equal to 0 otherwise. Then we can define n most 3 to the d plus 1 Boolean conjunctions. Why? Because we can define for xi whether this is positive, 0, so true or false, or just not included in the conjunction statement. And also y plus 1 here, we can define hx equal to 0 always. Okay. So there are at most 3 part to d plus 1 Boolean conjunction, and efficiently run over in realizable case. This is a property of this Boolean conjunction. So when there exists true hypothesis hx that satisfy all the training data point, then from the full condition, so just write down all the x1, not x1, x2, not x2, and so on, and sequentially deleting conditions that are not satisfied by each training data point. Then after go through all the training data point and data point, all the remaining condition will satisfy all the training data point, so we can easily make ERM solution, the hypothesis having 0 training error. Okay, but unfortunately again there is no algorithm efficiently find the best ERM if there is no such perfect hypothesis. Okay, so again, this is known as an NP hard. The last example is very interesting. We can define a hypothesis using three Boolean conjunction defined the previous slide page. So like this, hx is equal to a1x or a2x or a3x. Okay, when one of Boolean conjunction is true, then hx is true. Okay, then the cardinality of such hypothesis, the class of such hypothesis, is less than or equal to 3 to the 3n. So very huge size of hypothesis. But this hypothesis class is known as very difficult task, even with realizable condition. Even if the training data point has the perfect hypothesis having a zero training error, we still have trouble to find the best hypothesis having zero training error using this hypothesis class. Okay, it is very, very difficult to design very efficient approach that find the minimum training error hypothesis. But very interestingly, we can think DNF as a different form like this. Okay, every these three DNF hypotheses can be rewritten as follow: combinations of triple. Okay, combinations of triple. So we can think more bigger hypothesis class. Bigger hypothesis class means a superset of original hypothesis set. So this is superset of our hypothesis class, because every single hypothesis in our original hypothesis class is also member of new hypothesis class. So we can say that this new hypothesis class is a superset of original hypothesis class. Okay, so instead of using this original 3DNF hypothesis class, you can think all triplet of returns to Boolean, indicating whether it counts or not. Okay, then the number of hypotheses is 2 to n per to 3. So much bigger than 3 to the 3n. Especially n is huge, right? So this is superset of this. And using the superset, since the number of hypothesis member increase, people might think the ERM becomes more difficult. But very interestingly, we can more easily design efficient rule for this hypothesis class. Although the size of hypothesis increase, very interestingly, it becomes more easier to design efficient rule that require a lot less smaller computations compared to the previous case. Okay, so the one key message from this example is, if you think the learning process is very, very difficult, you can switch the gear to find another hypothesis class. Then maybe with another hypothesis class, you can save the computations.